So cylindrical cable, infinitely long. Infinitely long cable. And we calculate on this vertical axis its electric potential. R is the distance from the cable. Point A, VA is the question. Charge on the cable. Q. So its potential is the question. What is the electric potential of infinitely long cable? Of course, we use the same relationship, this one. So work done by electric field is the potential difference between 2 points. So I'm writing from R to infinity again. So we are checking with infinity. From R is the distance from the origin, R to infinity, electric field of the cable times dr equal VR minus V infinity. Now, cable's electric fields. So I will go back to week 5. I directly find its electric fields from my lecture notes. So we have already did this calculation, you remember, and finally we get this solution. Electric field of the cable, 2K lambda R. Yes, 2K lambda R. In week 5, we can use it. This is 2K. Because infinitely long cable, I cannot write Q, I'm writing its density, 2K lambda R. From week 5. I get this from week 5. So potential VR minus V infinity equals 2 from R to infinity, 2K lambda over R dr. So 2K lambda constant. This is ln R. ln R. Yes. Now, we had a problem. My problem is infinity. When I substitute infinity lambda R, yes, from R to infinity. So this solution gives approach to infinity, ln infinity minus ln infinity 2K lambda, 2K lambda, ln infinity minus ln. So we had a problem with this one. In the case, potential is not finite. So I cannot, of course, use this one because ln infinity means infinity, but potential should be 0 at infinity, right? So I have to solve this problem. To solve this problem, I'm changing my final position. I say that, yes, when we approach the infinity, potential is decreasing to 0. But this is a finite position. So I assume that this is the cable. So to solve this problem, to remove this infinity from my equation, I am choosing a critical point. For example, there is a position, let's say R prime. When I reach the R prime, potential is already 0. So potential is decreasing to 0 at R prime. After R prime, potential is always 0. So you don't need to go to the infinity because This is the cable. 1 kilometer, maybe 2 kilometers away from the cable, it's already zero. Okay, so R prime is a finite value and shows this critical threshold. So before R prime, potential positive, after R prime, potential zero. So it's decreasing to zero at a finite position. Where is R? R is this one. R is somewhere here. Okay, so from cable to the R prime, potential is decreasing. When we just reach to R prime, potential is zero at a finite position. So I will write again, I'm not going to infinity, I'm going to R prime. And I know at R prime, potential is zero. This is the solution, 2k lambda dr. In this case, this gives V R prime, VR minus VR prime. Yes. VR minus VR prime. Now 2k lambda ln R minus ln R minus ln R prime. I know this is zero. This is zero because R prime is a long distance, but finite. This is zero. Then VR, this is VR, potential of the cable at R, 2k lambda ln R over R. Yes, I am writing according to R prime. I am defining the potential according to R prime. R prime is a critical value, and we can find R prime with experimental measurement. With experiment, measure the R prime and find what is the R prime, at what position potential drop to zero. Otherwise, theoretically, if you approach the infinity, equation doesn't approach to zero. So we solve this problem with this technique. Another solution actually may be expanding ln function into the series. And maybe, I don't know. For example, let's say the Taylor series of logarithmic function. Taylor ln boom. Taylor series. This is sin x, for example. ln 1 minus x. Ln hepsi var, ln yok yani. Bunun hepsini vermiş. Hiperbolik, trigonometrik, geometrik, natural. Niye 1 minus x diyor? Neyse. Çok önemli değil. Boşver. Sonuçta, as a result, R prime, I have a critical reference R prime. My reference is R prime. At R prime, I know that potential doesn't change, drop to zero. So according to R prime, I am defining cable's potential. Yes, last one. Last one is K6, parallel plates. Infinitely large parallel plates. Parallel plates, electric potential. Electric potential. So you know what is the parallel plate? Two plates having the same charge density, sigma. I bring two parallel plates in free space, infinitely large parallel plates. Plus sigma minus sigma. So one is plus sigma, other is minus sigma. So we set an electric fields between them, uniform electric fields. This electric field strength is given by between them 4 pi k sigma. So that comes from week 5. Again, outside region, electric fields here 0, electric field here 0. So we have only electric field between two plates. Now, what is the potential difference between the plate? This is the question. What is the potential difference? So I'm writing potential of positive plate according to negative, also negative plate according to positive. Again, I'm writing this relationship. Integral electric field of the plates times dr equal V plus minus V minus. So I'm integrating the electric field of plate, but electric field of plate, as you know, constant. This is the constant field, 4 pi k sigma. So I can take this electric field out of the integral. So 4 pi k sigma times integral dr. What does it mean, integral dr? Distance between the plates. So this is d, distance d. Integral dr means, so we are integrating starting from the positive plate to the negative plate. This is d. So electric potential difference, V plus minus V minus, given by 4 pi k sigma d. Yes. Here is the potential difference. It's a very simple equation. Sigma is the charge density, d is the plate separation, k is the Coulomb constant. Let's give an example. If I have a charge density between the plates, sigma is, let's say, 3 microcoulomb per meter square. The charge between the plates, in either plate, 3 microcoulomb charge distributed in meter square area. So what is the plate separation? Plate separation is, let's say, maybe 3 centimeters. 3 centimeters. Actually, maybe less than the 3 centimeters. Less than the 3 centimeter, but let's say 3 centimeter. Then sigma is this one, k, d. So if I substitute these values in the equation, so delta V, potential difference, that means V plus minus V minus, 4, 314, 9, 10, 9, Coulomb constant, sigma, 3 times 10 minus 6, Coulomb meter square. This is centimeter, 3 times 10 minus 2. Yes, if I take all of these numbers, what is the potential difference between the plates? Only 10 comes from here. 9, 9, 8, 81, 4, 3, 14, 810. 4, 3, 14, 3, 14 times 810. 10,173. 10,173 volts, 0.6 volt. As you see, there is a huge electric potential, high voltage between the plates. And even if we say that the sigma is, yes, sigma is low, but it doesn't matter. Because of distance of 3 centimeter distance, when you set 3 centimeter distance and uniform electric field, you have to apply a huge voltage. That shows. Because 3 centimeter for uniform electric field is very big distance. Imagine your battery. What is the thickness of the battery? And what is it between the plate, distance between the plates? Okay. For example, let's calculate our battery. 5 volt, we know 5 volt. Battery is 5 volts, right? So battery, phone battery, 5 volts. If I apply the equation 4 pi, 9, 10, 9, I don't know sigma, I don't know thickness, let's say sigma d. Let's find the sigma d, this factor. So what is sigma d? I will divide numbers. So 5 over 4 over 9 over pi. It's 0.04, yes, 0.04, and here is the 9. So sigma d is given by 0.04 times 10 to 9. This factor. So you can understand, for example, what is the thickness? You can predict the thickness and predict the sigma in our battery. Okay, so we can only calculate for our battery sigma times B factor, this coefficient. So if you know sigma, you can predict thickness, or if you know the thickness, you can say what is the charge density as you see nanocoulomb. Not too much. Okay, nanocoulomb per meter square charge distribution. Okay. Bu kadar yeter değil mi? Yorulduk artık. 6 tane şey. Next Tuesday, we will continue with. Actually, I have one more topic. This electric field potential regulation also in differential form. Then we start capacity. Actually, I can give now, but I don't want to give. I'm very tired. You are tired.